Welcome to today's lesson on natural versus anthropogenic causes of climate change. In this lesson, we are going to explore a really important question. What is driving our changing climate? Earth's climate has changed naturally for millions of years. There have been ice ages, warmer interglacial periods, changes in solar energy, volcanic eruptions, and long-term orbital cycles. But today, scientists are clear that the current rapid warming is mainly caused by human activity. So this lesson is about comparison. We need to understand the natural causes of climate change, such as Milankovitch cycles, solar variation, and volcanic activity. Then we need to compare those with anthropogenic causes, which means human-caused changes, especially the release of greenhouse gases. By the end of the lesson, you should be able to explain that climate change is not always caused by humans, but current warming is strongly linked to human activity. Let's begin with our learning objectives. By the end of this lesson, you should be able to do three things. First, you should be able to explain the three Milankovitch cycles and how they influence global temperature. These cycles are long-term changes in Earth's orbit and axis. They affect how much solar energy reaches different parts of the planet. Second, you should be able to assess the impact of solar variations and volcanic activity on the climate. Solar variation means changes in the sun's energy output. Volcanic activity can affect climate by releasing ash and gases into the atmosphere. Third, you should be able to differentiate between natural cycles and anthropogenic climate change. Anthropogenic means caused by human activity. The key skill today is being able to say, yes, Earth's climate changes naturally, but the current pattern of warming is different in speed, timing, and cause. So throughout the lesson, keep asking yourself, is this climate change natural, human-caused, or a mixture of both? Before we go further, let's look at the key vocabulary. The first word is anthropogenic. Anthropogenic means originating in human activity. For example, greenhouse gas emissions from burning coal, oil, and gas are anthropogenic because they are caused by people. The second word is eccentricity. Eccentricity is the shape of Earth's orbit around the sun. Over long periods of time, Earth's orbit changes from being more circular to more elliptical or oval-shaped. The third word is insolation. Insolation means incoming solar radiation. In other words, it is the amount of solar energy reaching a particular area of Earth. These words are important because today's lesson is about causes. We need to understand what affects the amount of energy Earth receives and what affects the amount of heat Earth keeps. Before we look at why climate changes, let's recap how we know climate has changed. One of the strongest pieces of evidence comes from ice cores. Ice cores are like frozen time capsules. Scientists drill deep into ice sheets in places such as Antarctica and Greenland. Each layer of ice represents snowfall from the past. Tiny bubbles of ancient air are trapped inside the ice. By analyzing these bubbles, scientists can measure past concentrations of gases such as carbon dioxide and methane. This is called proxy data. Proxy data means indirect evidence. We did not have thermometers hundreds of thousands of years ago, but natural records such as ice cores and tree rings allow scientists to reconstruct past climates. Ice cores can also be used to study oxygen isotopes. The ratio of oxygen isotopes in the ice helps scientists estimate the temperature of Earth when that snow originally fell. So before we ask what causes climate change, we need to remember that scientists have evidence showing how climate changed in the past. Let's do a quick recall check. Question 1. What is the term for a natural recorder of past climate, like ice cores or tree rings? Question 2. What specifically is trapped inside ice cores that scientists analyze? Question 3. True or false? The current Holocene epoch has seen higher carbon dioxide levels than at any point in the last 800,000 years? Take a moment to think through your answers. Remember, proxy evidence does not give us direct thermometer readings. It gives us indirect clues about past climate. Let's go through the answers. For question 1, the answer is proxy data. Proxy data is indirect evidence of past climate, such as ice cores, tree rings, pollen records, and historical documents. For question 2, scientists analyze air bubbles, or gas bubbles, trapped inside ice cores. These bubbles contain samples of ancient atmosphere, which can show past greenhouse gas levels. For question 3, the answer is true. Carbon dioxide levels in the current Holocene epoch have risen higher than at any point in the last 800,000 years. This matters because it gives us a long-term comparison. We can see that today's greenhouse gas concentrations are outside the natural range recorded in ice cores. Now let's look at the first major natural cause of climate change, Milankovitch cycles. Milankovitch cycles are long-term changes in Earth's orbit and axis. They affect how much solar radiation reaches Earth and how that radiation is distributed. The first cycle is eccentricity. Eccentricity is the shape of Earth's orbit around the Sun. Sometimes Earth's orbit is closer to a circle. At other times, it becomes more elliptical or oval-shaped. This cycle happens roughly every 100,000 years. When the orbit is more elliptical, Earth's distance from the Sun changes more during the year. According to the slide, when Earth's orbit is highly elliptical, Earth spends less time close to the Sun, which can contribute to cooler global temperatures and potentially help trigger glacial periods. The key point is that eccentricity affects the amount and distribution of solar energy Earth receives. However, this is a very slow natural process. It happens over tens of thousands of years, not decades. Now let's look at the other two Milankovitch cycles, axial tilt and precession. First, axial tilt. Earth is tilted on its axis. This tilt changes over long periods of time, between about 22.1 degrees and 24.5 degrees. When the tilt is greater, seasons become more extreme. That means summers can be hotter and winters can be colder. When the tilt is smaller, seasons are less extreme. This matters because if summers are cooler, winter snow and ice may not fully melt. Over time, this can help ice sheets grow. Now let's look at precession. Precession is the wobble of Earth's axis, a bit like a spinning top. This cycle takes about 26,000 years. Precession changes when seasons occur during Earth's orbit. For example, it affects whether a hemisphere's summer happens when Earth is slightly closer to or further from the Sun. Together, eccentricity, tilt, and precession help explain long-term glacial and interglacial cycles. But again, the important point is timescale. Milankovitch cycles are slow. They cannot explain a sharp global temperature rise over just 150 years. Now let's look at another natural factor, solar output. The Sun is the main source of energy for Earth's climate system, but its energy output is not perfectly constant. One sign of solar variation is sunspots. Sunspots are dark, cooler patches on the Sun's surface caused by intense magnetic activity. It might sound strange, but periods with more sunspots are often linked to slightly higher solar output overall, because the surrounding areas can release more radiation. Sunspot activity tends to follow an 11-year cycle. The slide also mentions the Maunder minimum, which lasted from about 1645 to 1715. This was a period of very few sunspots, and it coincided with part of the Little Ice Age in Europe. This suggests that solar variation can influence climate. However, solar variation is not enough to explain modern warming. The changes are relatively small and cyclical, while modern warming has been rapid and strongly linked to rising greenhouse gas levels. Now let's look at volcanic activity. Volcanoes can affect the climate, but often in a cooling direction. Huge explosive eruptions can blast ash and sulfur dioxide high into the atmosphere, especially into the stratosphere. Sulfur dioxide can form tiny aerosol particles. These particles reflect some incoming sunlight back into space. This reduces insolation, which means less solar radiation reaches Earth's surface. As a result, global temperatures can temporarily fall. This cooling usually lasts around 1 to 3 years, depending on the size and type of eruption. So volcanic eruptions can cause short-term global cooling. However, this is different from modern climate change. Volcanic cooling is temporary, while current global warming is long-term and linked to increasing greenhouse gas concentrations. Now let's sequence the process of volcanic cooling. The stages are: global average temperatures drop temporarily. Insolation is reflected back into space by the aerosol particles. Ash and gas reach the stratosphere, forming a thin veil. A massive explosive eruption releases sulfur dioxide gas. Think carefully about cause and effect. First, there has to be a volcanic eruption. Then ash and sulfur dioxide reach the stratosphere. Then the particles reflect incoming solar radiation. Finally, less energy reaches the surface, so global average temperatures drop temporarily. The correct order is: first, a massive explosive eruption releases sulfur dioxide gas. Second, ash and gas reach the stratosphere, forming a thin veil. Third, insolation is reflected back into space by the aerosol particles. Fourth, global average temperatures drop temporarily. This is a good example of a natural cause of climate change. But notice that the effect is usually temporary cooling, not long-term warming. This helps us compare natural and anthropogenic causes more clearly. Now let's move from natural change to anthropogenic change. Anthropogenic means caused by human activity. Since the Industrial Revolution, humans have greatly increased greenhouse gas emissions. This has created the enhanced greenhouse effect. The natural greenhouse effect is essential for life. Greenhouse gases trap some of Earth's outgoing heat, keeping the planet warm enough for living things. But the enhanced greenhouse effect is different. It happens when humans add extra greenhouse gases to the atmosphere. The biggest cause is burning fossil fuels, such as coal, oil, and gas. These fuels contain carbon that was stored underground for millions of years. When we burn them, that carbon is released into the atmosphere as carbon dioxide. The problem is that we are releasing stored carbon faster than natural systems can absorb it. As a result, more heat is trapped in the atmosphere and global temperatures rise. Now let's compare natural and human-caused carbon change. The slide refers to a graph showing carbon dioxide levels over 800,000 years. For most of that time, carbon dioxide levels rose and fell with natural glacial and interglacial cycles. But at the end of the graph, there is a sharp rise. This is often described as a hockey stick shape. The rise is very steep compared with past natural changes. The slide explains that anthropogenic carbon dioxide is now rising 100 times faster than at any point since the last ice age ended. This matters because speed is one of the key differences between natural and human-driven climate change. Natural cycles happen slowly, giving ecosystems more time to adjust. Human-driven greenhouse gas increases have happened extremely quickly, especially since industrialization. So the graph helps show that modern climate change is not just another normal cycle. It is a rapid human-driven anomaly. Now let's test your understanding. The statement says, climate change is always caused by human activity. Is that true or false? Take a moment to think. We have already seen that Earth's climate has changed naturally for millions of years. Milankovitch cycles can help cause ice ages and interglacial periods. Solar variation can influence temperature. Volcanic eruptions can cause temporary cooling. So climate change is not always caused by humans. But that does not mean current warming is natural. The key is to separate long-term natural climate change from today's rapid anthropogenic warming. The statement is false. Climate change is not always caused by human activity. Earth's climate has changed naturally for millions of years due to orbital cycles, solar variation, volcanic eruptions, and other natural processes. However, current warming is mainly human-driven. The correct explanation is, Earth's climate has changed naturally for millions of years due to orbit and volcanoes, but current warming is human-driven. This is an important distinction. A weak answer might say, climate change is natural, so humans are not responsible. A stronger answer says, climate change can be natural, but the current speed and pattern of warming points strongly to human activity. The correct answer is B. Earth's climate has changed naturally for millions of years due to orbit and volcanoes, but current warming is human-driven. Option A is wrong because humans are not the only things that can change carbon dioxide levels or climate. Natural processes can affect climate too. But the evidence shows that modern warming is different. It has happened rapidly since industrialization. It matches the sharp rise in greenhouse gas emissions. And natural causes alone cannot explain the current temperature increase. So the key conclusion is, natural climate change exists, but modern global warming is anthropogenic. Now let's bring everything together with the summary challenge. The question is, if natural causes like Milankovitch cycles and sunspots are always happening, why are scientists so certain that current warming is anthropogenic? This is asking you to compare evidence. First, natural cycles happen over long timescales. Milankovitch cycles take tens of thousands to hundreds of thousands of years. They cannot explain rapid warming over just 150 years. Second, carbon dioxide increases aligned closely with the Industrial Revolution. As humans burned more coal, oil, and gas, atmospheric carbon dioxide rose sharply. Third, solar output does not explain the warming trend. If the sun were the main cause, we would expect solar output and temperature to rise together. But the slide notes that solar output is falling while temperatures rise. Fourth, climate models show that natural factors alone cannot explain the current temperature spike. When human greenhouse gas emissions are included, the models match observed warming much more closely. So scientists are confident because multiple lines of evidence point in the same direction. You might have said that natural cycles span millennia, while current warming has happened in around 150 years. That is a strong point. You might also have said that carbon dioxide increases align with the Industrial Revolution. That is also important. You might have said that solar output is falling while temperatures rise. That weakens the argument that the sun is responsible for modern warming. You might also have said that climate models show natural factors cannot explain the current spike. A strong GCSE answer might say, scientists know current warming is anthropogenic because natural cycles, such as Milankovitch cycles, happen over thousands of years, while modern warming has happened very rapidly since the Industrial Revolution. Carbon dioxide levels have risen sharply as fossil fuel use has increased. Solar output cannot explain the warming because temperatures have continued to rise even when solar output has not. Climate models also show that natural factors alone cannot explain the current temperature increase. That answer is strong because it compares natural and human causes and uses evidence.